So, in this lecture, we will look into planning. So, till now, what we have seen in this course is the primary thing that we have seen: search, CSP, propositional logic. We have seen temporal logic also. We have not seen, but we will see in later class. And in this lecture, we will see planning. The main idea in artificial intelligence are the primary ideas for artificial intelligence is the search technique and the logical deduction that we have seen. So in the search, what we have seen, we are in a start state. We define the state in a kind of a generic manner, and we will have a goal state where we want to reach, and we would like to find a path from the start state to the goal state. And for every state, whatever state we have, in every state we will have some action, and once we apply this action, this basically give me a new state. So that was the state transformation rule that we have already seen. So that was the basic idea for search. In CSP, what we have done, when we are in a given state and we have been given a set of constraints, we try to find out, we try to encompass more number of things, or we try to discard some of the stuff which are not valid so that we can reduce the search space. So that was the main objective. So when we do the arc consistency, node consistency stuff, we actually do not change the state, but we try to discard some of the stuff. So in that sense, we can say that we expand our horizon, which belongs to the same set of states. So we are basically discarding certain things, and we are exploring in an efficient manner. In propositional logic, it was again the same thing. So we have been given a knowledge base, and from that knowledge base we try to identify what are the other things that can be concluded. So here we do not explore any other new state, because based on the knowledge base we try to based on the knowledge base we try to deduce some other information, but we do not change the states of the system. In temporal logic, what we have seen that if we want to specify this knowledge base, or if we want to specify some proposition over time, so that required some kind of a augmentation of the proposition logic, and we have seen this temporal logic for that part. Probabilistic reasoning we have not seen, but the idea is like if you have some information, like if I say P implies Q, but with a probability of 0.2 or maybe with a probability of 0.8, then how we can analyze the system behavior. So if we try to associate some kind of uncertainty between two events, and if it's a complex system, then there will be a lot of dependency, and if we need to identify certain kind of things, then we require a separate kind of methodology through which we can actually answer those queries. So that was probabilistic reasoning. So we will see in the upcoming lectures. And the next thing that the important thing that will be looked into in this lecture is planning. Now here the idea is that we try to mix the search and the propositional logic, or we can say a kind of a logic that we want to introduce. So what we have here in original search we try to specify the states in an explicit manner, but in this case when we solve the planning problem we specify the states involving logic. So we have seen the proposition logic or the predicate logic, so we are not changing any of the states, but we are representing one such state. Based on the knowledge base we can derive some information or we can deduce some information out of that stuff. Now if I allow some action on this knowledge base that will change the state, and then we try to reason the whole stuff, that actually leads to a kind of a problem called planning, and we will see what are the applications and how we can do that stuff. So the basic idea here is we try to combine the logic as well as the search in a certain class of problems, because if we try to solve this set of problems using the basic search that we have seen, so sometimes it becomes not a useful, or that actually performs pretty poorly, so that we try to develop a specialized methodology for different set of application. Now if we look into some of the real world situation where we can actually apply this kind of planning, like we have to plan for vehicle navigation, like robotic movement. Like say if I have a robot here and it needs to move to this place, so but there may be some kind of a obstacle here. In certain places there are some obstacles, so what it needs to do is it needs to choose a path which avoids this obstacle and can reach to the destination. So how it can find out that path, or how we can represent the state and all sorts of stuff, so that that we will see, and the basic algorithm will be also looking into. Then travel planning, process control, assembly line, and many other operation you can actually figure it out. So and in the very first class what we have told, if you remember the problem missionaries and cannibals, that there is a one boat available here, and there are 3 missionaries and 3 cannibals, and the goal is to move all these 6 stuff on the other side of the river. Only one thing is that at no point of time there will be a situation where a missionary is dominated by the cannibals. Like I cannot have a situation where I can keep 1 missionaries and 2 cannibals here, and on the boat I can carry only 2 person at a time, at most 2 person at a time. So how we can find out what could be the strategy so that I can move all these 6 people on the other side of the river. So this kind of problem can be addressed through planning problem, and we will see. Now let us take a very simple example. Let's say we want to build an agent which will get me milk, bananas and a book. Now whenever we say any AI based agent, that means it will be kind of a rational agent. I can say something, or I expect that my agent will act intelligently and it will do the job. So when I ask my agent to do this thing, So I need to develop a methodology for that, how such problem can be solved. Now the thing is, when I want all of this thing, so in the initial state, like in the initial state, I will not have milk, I will not have banana, and I will not have a book. Because if I do not have anyone, if I do not have all these three things, then only I can say that get me milk, bananas, and a book. And probably my agent is at home and it is without milk, bananas, and book. And the goal state, like when I say that get me milk, bananas, and book, the goal state will be agent is again at home, but now it will have milk, bananas, and book. So so this is my initial state and this is my goal state. Now the thing is we have to move from initial state to the goal state. Now if I want to move to the goal state, then we have to have a set of actions, because through these actions we can change the state of the system. Now we have to define a set of actions for that. For example, in this case, let us define action like buy X, which will mean buy item X. X can be any one of these three. I can have a action something like steal X, and it means I can steal X from somewhere, and also I can say go to X, that means move to location X. So where this location can be market, or can be home, or can be library, or some other thing. Now if I have this set of moves, then I can say, or my agent can execute this stuff, like it can say like go to market and then buy milk, buy book, then steal banana, then go to home. So if the agent performs this operation in sequence, then it will achieve everything and then it will reach to home. Now this is a simple thing, so we can easily identify what steps can be taken or what action can be made, so that we can reach to a initial state to the goal state. But if you have, say, large number of states and there are a lot of dependencies, we will see what does that mean. But in that case, finding out these moves is not so trivial. So the whole objective here is that we will have a initial state, we will have a goal state, we will have a set of moves that will be my the input specification, and there will be some more thing that we will see. And once we have this information given to us, we would like to generate a set of moves that should be executed, or set of action that needs to be made from the initial state, so that we can reach to the goal state. So if you look into this problem, so it appears to be similar to the search problem, but there are some difference, because when we solve this problem, we solve it in a different way. So we will see that part. So the basic planning problem is to generate one possible way to achieve a certain goal from a given initial situation, and the given set of action. So that we have described here. So we have this initial state, we have the goal state, we have the moves, and we have to generate this thing. So that was the simple problem or the basic problem. And this, if you look into this problem, then it's nothing but a search problem. I have the start state, I have the moves, we know the result of moves, that means the state transformation rule, and we have the goal state. So target is to reach from start state to the goal state. So it appears to be exactly same as search problem. Yes, it's a search problem, but when we typically solve this problem, we try to use a goal directed methodology. That means if you remember the search problem, then we start our search from the start state, and then we expand our horizon, we explore new state, from there we start again exploring new states, and so on and so forth, and then we reach to the goal state. But in this case, when we solve the planning problem, often we will start from the goal state, and then we will try to expand, or we will try to reach to the start state, or maybe we can do in a both way manner. So I will take few steps from the start, and we will take few steps from the goal, and we will try to combine these two things. Or we can start from the goal also. Just in the goal state, something has to be true, we will try to see how we can fulfill those things, and then we can proceed in that manner. And there are a few other things that we have to see. Like if you remember the problem that was describing, like get milk, bananas, and a book, then we have a start state, and from the start state we can apply different kind of moves. Like we can go to market, we can go to school, go to hospital, go to bookstores, have bananas, and many more we can have. So once we apply this action or the moves, we reach to a new state, and on that state we apply another action, we reach to another state. We apply another, if we apply another action, we will reach to another state, and so on and so forth, and eventually we will reach a finished state. So now the target is to find out a path so that we can reach to the finished state. Only thing, in the finished state we have to ensure that whatever was the requirement, that is fulfilled. Now the planning and the search, definitely it is a search problem, but it's a specialized search on a particular domain. We use this kind of technique. So the thing is, when we have this set of actions, these actions have requirements and consequences that should constrain applicability in a given state. So typically when we look into the search, we have all the actions available, but when we have the planning, all actions may not be available, because if you are at hospital, probably you can buy medicine, but if you go to market, then you cannot have an option like buy medicine. I am assuming that there is no medicine shop in the market, or some other things that can actually so there will be some restricted set of actions may be available. And in this scenario, when we look into a practical system, in these actions actually can be very, very restricted also. And another important observation was, like when we look into any practical problem, then most of the real world problem has lot of independent components. So there may be lot of parts, and these parts can be solved as an independent manner. So so the thing is, if we have a goal where we can identify the sub goals and we can achieve those sub goals independently, and if we achieve those sub goals independently, that can help us to identify one such path easily. And then when we look into this stuff, or when we work in a practical environment, that we work in a goal directed manner. So when we have a target to reach to a goal state, it has some requirements. Then we try to look into the target, and then we try to find out the plan. Like if I need to have milk, banana and book, then I would like to think in this way, that where can I get bananas? Okay, it's in market, so I have to go to market. So that way we can decide. So I look my requirement, have banana, so where can I get banana? It's the market. So I have to go to market. Where I am right now, I am at home, so I have to apply a move like go to market. So that way we can actually solve a planning problem. It's a search, but it's when we solve in a different manner. So when we have this planning system, so it basically does the following. It unifies action and the goal representation to allow selection in an unified manner. So we try to represent the action and the goal in a kind of a logical language, so that we can apply these two things in a compact manner. We will elaborate with the example what does that mean. And the other stuff like divide and conquer by sub-goaling, because like if I want to have banana and if I want to have milk, then these two are my sub goals, and we would like to achieve these two sub goals independently. And it actually so this kind of stuff is a relaxed requirement for sequential construction of solution. So when we go ahead with this sub-goaling, we try to find out some ordering of the stuff. So we try to achieve the sub-goals independently, so which is kind of a relaxed requirement for sequential construction of the solution. So that means we find out possible path independently, and then we combine those paths so that we can achieve the final goal. So in order to represent this set of problems, we use a language called strips, or a variant of strips mostly. It was one of the first proposed language for the planning, was developed in a Stanford University, and many planners as of now today use this kind of language or a variant of this one. So we will look into one such example just to get the idea, not into the exact language, but how we can represent a planning problem in this set of stuff. So as you know that we have to represent the state, and this state we are going to represent using some kind of a predicate or some kind of a propositional logic. So these states will be represented as conjunction of propositions. For example, like we said that we need tea, we need to have bananas, and we need to have a book, and my agent should be at home. That is kind of an example, like it was the initial state, like I am at home, or the agent is at home, and I don't have tea, don't have banana and book. So this was the initial specification, or I can represent a state in this form. So it is the conjunction of the propositions. And assumption is like atoms that are not present are treated as false. So if I have not specified something, like I have not specified not at market, so effectively, since I do not have specified anything at market here, so effectively this will be treated as false. That means not at market is true. Now when we have this action basically can be distinguished by its name, but the interesting thing is that this action will have more information. What are those information? It will have a precondition and it will have an effect. So precondition again will be conjunction of literals. So something of this sort of stuff, this kind of expression that we will have, and effects will be also conjunction of literals. So we represent the state, we represent the action in the similar manner, and the effect, the outcome will be also represented in the similar form. Like for example, if I have an action like go to market, then probably a precondition could be at home. If I am at home, then only I can go to market. If I am market, then go to market has no meaning. And this is my precondition. And once we apply this action at a given state where this precondition is true, then the effect will be I am at market, or my agent is at market. So the idea is follows, like when we apply an action at a given state, the state should satisfy this precondition, and if it satisfies the precondition, if I apply this action, then the results will be given by this effect, or the changes that will be made on the state that will be reflected by this effect. So that was our action, and once we have this set of actions, then our main target is to find out a solution for the problem. So this solution will be a set of planned steps, and each step is one of the operator for the problem. So in each step it will be one of the operators for the problem, means we will be applying one such action. And this will, so what we need to do, we need to order these steps based on some constraints. So what kind of action we can actually apply, and in each ordering, constraint is of the form Si to Sj, indicating that this must occur first, then only this can occur. So whatever moves that I have got, I have to order all those moves, that this occurs before this occurs before that, and so on and so forth. So that we will see how to do that. Now let us look into some example. Let's say we have a flight operation where we have a flight from, or we have a plane that should go from one location to the another location. So how we can specify such an action? This is just an example. Like say we can define a action called fly, and we can use the predicate logic notation, like it is the plane ID that moves from the CT from to the CT to. So that was our action notation. Now if I need to apply this action, then it has to be, there should be some kind of a precondition. So the precondition is, for an example, that the plane ID or the plane should be in the from CT. so here at plane ID form means that plane is at city named from, and there is a airport in the from city, there is a airport in the to city also. If these conditions are satisfied, then I can apply this action, and then once we apply this action, the result will be that plane ID is no longer belongs to in the from city, and this plane will belong to city now because it has moved to a new city. Now every action has some kind of a precondition and effects, and when we try to apply any action, we have to check for the precondition, and so we can apply a particular action if the state satisfies the precondition, and the effects will be once we apply that action, then what is the final outcome. Now if you look into the initial state, it will not have any precondition as such, and if it is the goal state, then you will not have any kinds of effects after that one. So actions will be guarded with precondition and the effects. So let us take a concrete example. Like we want to transport some cargo involving loading and unloading and flying it from one place to another place. So something similar to the previous one, but now what we need to do, we have to load some cargo, we have to unload some cargo, and we have to fly from one city to another city. Now if you want to model this problem, and let's take a concrete example. Let's say I have a cargo C1 at Calcutta, I have cargo at C2 at Delhi, I have I have a plane 1 at Calcutta, and I have a plane P2 at Delhi. So that was my initial configuration of the state, and that state has been represented using this predicate model. Now the thing is, this is my initial state. Now let's say my goal state is I want this C1 to move to Delhi. So cargo 1 needs to move to Delhi, and cargo 2 needs to move to Kolkata. So I need to take some cargo from Kolkata to Delhi and some cargo from Delhi to Kolkata. Now, so that will be my goal state. Now, one of the thing here, we represent the state using predicate logic. It has some advantage. Like if you look into the whole system, then there will be other city, other cargo, flight is flying from one place to another. Since we are not using that stuff, we are not bothered about that stuff, we are not incorporating in our state definition. If it is a normal search problem, probably we would have been included everything on the state representation, and then the actual method can actually get exploded. The representation can get actually exploded. Now, so we have this initial state, we have the goal state, we have to define the actions. So we are defining an action load, which is loading of cargo to a plane at a given airport, because I cannot load a cargo something on a plane which is at another airport. So this is my action, and the precondition is that cargo needs to be in the airport A, plane also needs to be in the airport A. And once we apply this load action, then effectively we can say that cargo is not on the airport as such, not on the airport, but cargo is on the plane. So that was the thing that we can actually specify. Now, so that was the load. Similarly, for unload, it will be the reverse one. So if a cargo is on plane P and P is at A, on the airport A, then we can apply this unload function, and if we apply this unload, then the cargo is available on the airport and this cargo is no longer available on the plane. Now coming to another action like fly. So this fly P from 2, which is something similar to the previous one. So so plane P needs to be on at the from city, and once we apply this thing, so P is no longer at the from, but P is available in the to city. And we have discarded the extra stuff that we have seen in the previous slide, where we have talked about like there is an airport available or no airport is available, all sorts of stuff. So because if we introduce those things everywhere, we have to specify those things, and which is not required for us, so we can discard that thing. Now this is the these are the actions available. We are in this initial state and we have to reach to the goal state. That was our objective. So the final solution that you would like to create will be a plan, and this plan will basically tell us that what are the moves or what are the actions we need to make. Now in order to do that stuff, so we can say that you load cargo on plane 1 at Calcutta, you fly this plane P1 from Calcutta to Delhi, then you unload the cargo 1 from plane 1 at Delhi, and so on and so forth. And you can load cargo 2 on P2, then Delhi, then you fly again, then you unload the stuff. So if you do this set of operations on this initial state, then you will definitely reach to the goal state. Now for a planner, the objective is to identify this plan. So how can I find out this plan? So this set of actions or the sequence of actions that I need to make, then so what are the sequence I need to make so that I can apply this set of actions on the initial state and I can reach to the goal state. So that was the main motivation for this thing. So let us look into another examples, like we have to change a flat tire with a spare one. So the initial state probably we can describe in this manner. So tire is flat and I have a spare tire, and this flat tire is on the axle right now and spare is on the trunk right now. So that was my initial state, and the goal state will be spare should go to the axle. That was the thing that we need to specify. Now the actions which are actually available to me is, let's say, remove one object from one location. Now, what could be the precondition for this? So, precondition could be like this object should be in the location, then only I can remove that object. And once we remove that object, so what will be the effect? This object will be no longer in location. So that was the stuff. And this object will be lying on ground as a post effect. So I remove that stuff, so I keep it on the ground. There can be another action like put on. So put on T on axle. So some T on the axle. So the precondition will be like it is a tire T that we want to put, because we should not put any other object, and T is on the ground, and flat tire, it's not the flat tire on the axle. So flat tire is not on the axle, and some tire T is on the ground, and T then only I can apply kind of this action. And once we apply this action, T will no longer be on the ground, and finally T will be on axle. So here we are representing with a variable, so I can apply for any object that are available to me. And finally we operate only on the object tire T. Now the plan that we need to prepare here is like, you can guess, like we have to first remove the flat tire. Now once we remove this flat tire, then we have to remove the spare from the trunk, and then we can put the spare on the axle. So if we apply this set of stuff, then we can reach to this state. Our goal is that given an initial state, given a goal state, given a set of actions, how we can generate these plans which will make this initial state to the goal state. So that is our primary objective for when we solve a planning problem. So with this I will stop now. We will, in the next lecture, we will see how we can identify this plan, because today what we have seen, that we have just introduced the problem, and then we have to find out this plan, because if we cannot find out this plan, then it makes no sense, because we are not doing anything productive. We have to find out this set of plans. In the next lectures we will see how we can find out this set of plans given this information to us. So thank you very much.